To charge an electric vehicle from a standard wall plug, the alternating current needs to be converted into direct current. That job falls to a piece of hardware called the Onboard Charger, or OBC. Look at this circuit board. This is a typical OBC. The thick copper toroidal inductors and massive capacitors shown here create a heavy, bulky component that drives up manufacturing costs. Automotive engineers face a massive dilemma. They need to strip away vehicle weight to squeeze out more driving range, but they cannot eliminate the hardware that lets owners charge at home. The solution is the integrated onboard charger. Rather than carrying a dedicated converter, it reuses the car's traction motor and inverters. When parked, specific switches flip, reconfiguring the internal copper windings. This temporarily turns the propulsion system into an electrical charging transformer. By sharing these heavy-duty parts, manufacturers eliminate the redundant OBC. The vehicle drops significant weight and cost while still maintaining its ability to charge from a standard AC outlet. But when we move away from the driveway and plug into high-powered DC fast-charging hubs, pulling massive amounts of energy introduces a problem: poor power quality. EV fast chargers act as nonlinear loads. Instead of drawing power in a smooth, continuous wave, they gulp electrical current in violent, erratic pulses. These erratic pulses inject electrical harmonics and high-frequency supraharmonics, essentially aggressive electrical noise, backward into the local utility grid. This harmonic friction generates severe, concentrated heat inside the metal cores of neighborhood transformers, causing them to vibrate and eventually fail. When multiple vehicles charge at once, these overlapping harmonic frequencies can synchronize, amplifying the dirty power to critical, unmanageable levels. Look at this massive desert solar installation in California. When paired with high-capacity EV charging, engineers measured the total harmonic distortion spiking over 13%. Faced with distortion that high, utility companies are left with terrible options: either forcefully throttle the transformer capacity by 50% to prevent fires, or face total shutdown. The engineering solution to prevent grid meltdowns is a device known as an active harmonic filter. Think of this filter like industrial noise-canceling headphones. It monitors incoming dirty power waves from chargers in real time, mapping every single distortion. The moment it detects a spike, the filter instantly injects a precise anti-wave, shifted exactly 180 degrees out of phase. This active cancellation cleans the power instantly. As you can see with these standard utility pole transformers, the grid remains stable, allowing massive EV hubs to operate safely without blacking out neighborhoods. Now that we can safely pull massive amounts of power from the grid, the ultimate goal is pushing it back out. This is known as vehicle-to-grid bidirectional flow. There is a major logistical roadblock standing in the way. Millions of existing EVs were never built with the internal hardware or software designed to export their stored power. Older cars feature strict safety contactors that physically lock the high-voltage battery unless they detect a handshake from a legitimate charger. That leaves a vast reservoir of stored energy sitting uselessly during an outage. This prompted aftermarket engineers to develop a workaround to bypass the physical blockade. Their solution is the DC V2L tricking protocol, which operates through a specially designed external plug that goes right into the charge port. This external device fakes the complex digital handshake of a high-speed DC fast charge charger. The vehicle's computer is fooled into engaging the high-voltage contactors. The physical barrier drops and power flows backward, out of the battery port. This raw, hacked DC power is then safely routed into a standalone external inverter. Just like that, an older car becomes an emergency generator capable of powering a house during a blackout. The combination of IOBC part sharing, active harmonic filtering, and bidirectional tricking has expanded what an electric vehicle is physically capable of achieving. Look at this control room tracking the modern energy grid. These engineering workarounds integrate the electric vehicle directly into the global power network as an active two-way participant. But pushing a car's battery to do things it wasn't originally programmed for carries risks. What do you think about using aftermarket plugs to trick your EV into becoming a generator? Let me know your thoughts below.